Assalamualaikum and hi everyone. Welcome back. This is pre-recorded video 13 for chemical bonding. In the previous video, we have learned the introduction about VSEPR part 1. And please remember to differentiate between electron domain geometry and molecular geometry. I hope you still remember that VSEPR theory can be used to predict the shape of a molecule. The molecular shape is defined by the angles made between atoms. For example, 109.5 in methane, 107.0 in ammonia, and 104.5 in water molecules. Before that, can you differentiate between non-bonding and bonding electrons? Bonding electrons are electrons that are used for covalent bonding. The electrons in a bond are attracted by two nuclei and they do not repel as much as lone pairs. Therefore, the bond angle decreases as the number of lone pair increases. Okay, so this is water molecule has two lone pairs, so the angle is decreases 104.5. The repulsion between lone pair is the highest. Okay, the middle one is lone pair and bond pair, and the weakest one is bond pair and bond pair. This picture shows the position of lone pairs that influences the shape of a molecule. In A here, you can see the position of these two lone pairs in one plane repulse each other, making a seesaw shape. Okay, so the lone pair are here in one plane. You cannot see the lone pair. And in B, when the lone pairs are in vertical axis like this, so we will get a square planar. The differences in bond angles also include the type of bond, single or double or triple. We know that double and triple bonds have a greater electron density rather than single bond. So this affects the bond angle we can see between double bond and double bond has a bigger bond angle compared to single bond and single bond here. Okay, so 124.3 is bigger than 111.4. Okay, between double and single gets bigger angle. This slide shows you the steps to determine the electron pair and molecular geometry of a molecule. First, we need to draw the Lewis structure of the molecule. What we can do is count the total number of electron pairs around the central atom. In this case, is ammonia. The central atom is nitrogen. The second one is arrange the electron pairs in one of the above geometries, the geometries that you have learned before, to minimize electron repulsion, and count multiple bonds as one bonding pair. Okay, so the steps, this is step 1, step 2, step 3, and you can get actually molecular geometry as trigonal pyramidal, but the electron domain geometry is tetrahedral. So I've told you about the difference between domain geometry and molecular geometry. We can do some exercise here. Predict the molecular geometry for compound tetrachloromethane, ammonia, and H2O. It's very simple. Please follow the steps you learned in the previous slide. And yes, this is the answer. For tetrachloromethane, you will get geometry or domain geometry as tetrahedral. For ammonia is trigonal pyramid, and lastly for H2O is band shape. You can see the position of the lone pairs, and you are required to know the bond angle in this molecule too. Okay, let's try another molecules for SS4, ClF3, and xenon difluoride. You will get seesaw for SF4, seesaw molecular geometry for SF4. You will get T shape for CLF3. Okay, T shape for CLF3 and linear molecule for xenon difluoride. If you get any trouble getting these answers or find the logic behind this, please consult to your lecturer. Okay, last practice for this video. Let's predict the molecular geometry for octahedral arrangement for IF5 and xenon tetrafluoride. As mentioned in previous video, 6 electron pairs led to other molecular geometries. So you will get square pyramidal for IF5. And you will get square planar for xenon tetrafluoride. If you have problems understanding the materials in this video 13, please refer again to video 12 for better explanation. That's all the end for video VS EPR part 2. Thank you. See you in the next video.